Hey, what's up, guys? Okay, so this will be the probably the final video of primitive roots. So basically, in this video, that we are gonna to prove that we are gonna to prove that for r prime power, the multiplicative group is cyclic. This is important if you want to know that why Shaw's algorithm can work. That there are some technical detail. But algebraically, what we're going to show is that if P is R prime, then the cyclic group of P to the alpha, multiplicative group. So you take all the number which is modulo P to alpha, which is coprime to P alpha. You take it as a set, and this is a multiplicative group. This group is cyclic. And then we show that if alpha equals to one, this is true using you can prove that using basically the any finite field, right? So it's easy to show that if you know there's a finite field, and you take zero out, then this group will be cyclic. Okay, so there are like advanced proof on this, but let's say you don't know about some advanced algebra, so we can do it. We can prove it using the using some elementary tool. Okay, so there's a very simple lemma that I think it's trivial. So let me just write down, and you can do it as an exercise. By the way, if you like this kind of video, subscribe to my channel. So binomial coefficient. So P choose J, P divides P choose J for J from 1 to up to P minus 1. So let's P is upright. Okay, so the proof is very simple. You just write down this P minus 1 up to P minus J plus 1 divided by J minus 1 up to 1. So every factor below is less than J. So okay. Okay, so every factor below, right? Every factor below is less than J. So and P is a R prime power, so R prime, right? So there's no extra factor can cancel P. Okay, so which finish the proof. Okay, and if you know about this, then the rest will be very simple. So so there's a lemma. So this lemma say that if A and B are the same under the modulo P to V, so let's say V is greater or equal to 1, then if you do the power P, then this will increase by 1. Okay, and so this proof is basically using the same proof, using the lemma. So you just write down so you can just write down A equals to P to a nu times maybe X, right? And then you just do power P, so you get P to a nu X to the power P. And if you write down the binomial coefficient, that you're going to use P to the J, B to the J, P V X, P minus J, wherever J equals to 0, and P. Okay, so first term is B to the P. And let's say the rest of terms J from 1 to P, P, J, B to the J, P, V, P minus J, X, P minus J. So notice that there's an extra P here, right? So as we proved, there's an extra P here. And for each term, right? So for each term, we at least have P to a V term, right? So they're combined, they're a P to a V plus 1 term. So this is a proof. Okay, and more second, there's another lemma. So this lemma say that if A to a P equals to B to a P, modulo P to the nu plus 1. So say nu is great, so let's call it V plus 1 is greater or equal to 2. If then you can break this P. So you get A equals to P modulo P. So proof will be the similar as before. Okay. And I will leave an exercise that you can check why P equals 2 does not hold. So this is a simple exercise that you can check. But basically, if you believe what I say is true, that you just this binomial coefficient will give you the this lemma. Okay. So now the technical lemma is the following. So if A equals to B modulo P to the V, then we can have A P equals to BP modulo P to the V plus 1. Okay. And if also if A to the P equals to B to the P modulo PV plus 1, then we can get A equals to B modulo P to the V. Okay, so this is the lemma. Okay, okay. If you notice, know about this, then we're able to show the following. So this theorem, there is a primitive roots of let's say z to the p. Um, mm, let's using h. Okay, so let's go through a proof. So notice that. Let me just quickly say. So let's compute phi to the ph, right? So it's basically ph 1 minus 1 over p. So it's ph minus 1, p minus 1. So we need to find the element which order is basically as large as this. Okay, so right, so let's take R, which is coprime to P. So let's say GCD R P is 1 for arbitrary R. And let's say N is the order. Okay, so let's say the order of M. Let's say N is the order of R. Mm, okay, so this so let's say N is the order of R. Order of R. So what this says is that right, because the order of, so N must divide PH, P to H minus 1, P minus 1, right? So let's write N is, let's write N, let me just write, I can write N as P to the L times S, right? So since N divides this, so I can notice that L divides H, sorry, L less or equal to H minus 1, and S divides P minus 1. Okay, so let me just write down T. Let's say S times T is P minus 1. So T is just a stupid divisor. It's not important. Okay. Okay. So now okay. So let me just introduce a note. Let's say M is P to the H. Just for the convenience. So by definition, we have R to the N is 1 mod M. Because N is the order of R. Okay. So which means that R to the N to the T. So if we do the T power, that we get R to the P to L S and the T, which is R to the P to L S T. So which is one mod mod M. Okay, so this is trivial. But let's define alpha. Let's say alpha is R to the P minus 1. Okay, so notice that if I write alpha is R P minus 1, which means that R alpha to the what? To the P to the L is equals to 1 mod M. Because this is R P to the L S T, right? So and this is R to the P minus 1. So what I can do is that I know this is P minus 1, right? This is P minus 1. So so I can absorb this P minus 1 into this R. So I get R to the P minus 1 to the P to the L. So this is what true. And then this is P to H. Okay, so now here comes the powerful part. So we can use this theorem to split this L and this P to H. So we can apply this lemma and then we get alpha to the p to the uh so we can use this, right? But I know that L is less than or equal to H minus 1. So I can keep using lemma and finally I get alpha equals to 1 mod pH minus nu. Oh, okay. Minus this V. Okay. Sorry, minus this L. Sorry, I'm stupid. This is L. Okay. So I can keep using this lemma and split, and I get this. Okay. But now there's a problem, right? Because now there's a problem. Because that R's are alpha is RP minus 1, right? But alpha is 1 mod PH minus L. So I can pick. So suppose I can pick R to be the primitive roots of the P cross. So what it means that I can pick R to be this. So this means that R to the P minus 1 equals to 1 mod P. So this means that and this holds that when this guy is P minus 1. So this means that if I pick R to be the primitive roots of this guy, then this will force this H minus L can only be 1. Okay. Okay. So let me just maybe there is a technical detail. So let me just write down. So if I pick alpha this R is the primitive roots, it's primitive roots of the P cross, and also so this means that R to the P minus 1 is 1 mod P. And then also suppose I force that alpha sorry R to the P minus 1 is 1 mod, it's not 1 mod P squared. It's a simple exercise that you can prove that this R always exists. I know that there's a primitive roots here, right? But I can force that this R P minus 1 is not 1 modulo P squared. Okay, so this is true that I can prove. So if I find this R such that it satisfies these two conditions, then this condition holds will force H minus L equals to 1. So that means the L must be H minus 1. Okay, so that means that this number R already has an order that this L is already go to the highest possible one. Okay, so this is the first step, and after this step, that the rest is to like boost this R. So we can boost this R to force the rest to be P minus 1. Okay. So from this that I know that R to the P to the H ST, so S is 1 mod P to H, right? This is what we have before. But but I can keep using the split theorem, right? I can split to R to S equals to 1 mod P. Right? Sorry, this is H minus 1. So I split H minus 1 to this, then I get this. So the rest I just pick S. But there's nothing I can pick, right? Because if I use this theorem and up here, that by the definition, R is a primitive roots. R is a primitive roots, right? So this will force that S must be equals to can only be equals to the P minus 1. Okay, so this is a proof. So the proof idea is that I use this lemma. I use this lemma. And I pick R to be the primitive roots of this guy and satisfied additional conditions, this condition. Basically this proof just show that if you satisfy this one and the second one, that then you use a split theorem, then this will force that it are also be the primitive roots of the P to alpha. And the proof basically goes as follows as I just did. Okay, so basically this is the proof. Okay, so yeah, so
in the next video that we will show that this z to the p to the alpha cross also has a primitive roots. But this proof is almost trivial that once you know that there's a primitive roots here, you can construct primitive roots here from previous one. So if you notice this proof, then basically it's almost trivial. So now we show that the primitive roots theorem says that 2, 4p to alpha and 2p to alpha is cyclic. So these are the only cyclic group. Okay. And see you guys next videos.